What we're all about in statistics is figuring out what the chances are that we're going to be wrong, okay? We're never going to be 100% sure that we're right. We're never going to be 100% sure that we're wrong, but we're going to figure out what the chances are. How do we do that? Well, we have to make some assumptions. And the first assumption that we have to make is how that variable, whatever the characteristic is that we're talking about, we have to make an assumption about how that variable is distributed in the population. Okay? We have to kind of have a sense of how many people have high scores on it, how many people have middle scores, how many people have low scores on the thing that we're interested in. If we can make a sensible assumption about that, then everything else will just flow right from that. Let me use one particular distribution, the normal distribution. You've probably heard of the normal distribution many, many times. The normal distribution is usually represented by this lovely bell curve, and I don't claim to be a great artist in terms of drawing this thing, but nevertheless, you've probably seen this many times. You've heard about it in conjunction with how people might change the grades or curve the grades in a class and so forth. But the idea behind it is that these cases of whatever the variable is are distributed in a certain way, a very specific way in the population. That's the assumption that we're trying to make, okay? This is the bell curve, okay? In the bell curve, in the normal distribution, the most cases are right at the mean. So this is the mean of the variable, whatever it is, right? There's the most number of cases because that's where the highest point of the curve is. As you go away from the mean, you get higher or you get lower, there's fewer and fewer cases. That's what happens with something that's normally distributed. Let's take IQ as an example. Okay? In the population, let's say this is the mean of IQ right here. And most people are clustered around the mean. That's the highest point, and that's where most of our cases are. As we get higher, there's fewer and fewer people that have IQs in this range. So there's a lot fewer people who have these really super high IQs than there are people who are in here fairly close to the mean. Okay? Same thing on the low end. We have a lot of people right here in the middle. We have quite a few people here, but as we get lower and lower, there's very few people who have these really low IQs down here. Okay? That's how things are distributed in a normal curve. The normal curve, in fact, has some very specific kinds of characteristics to it that make the cases distributed in the same way every single time. If something is normally distributed, it's always going to have these characteristics. Okay? So if we calculated the mean and we calculated our measure of dispersion for the normal curve, the standard deviation, we would find out that a certain percentage of the cases is within certain standard deviations away from the mean, okay? So for example, if I calculate, whatever the score is, if I go out one standard deviation unit from the mean higher, and I go one standard deviation unit lower from the mean, then in here, there's going to be 68% of the cases. 68% of all of the people are going to be within one standard deviation unit above and below the mean, this whole area right in here. So 34 are going to be above, 34 are going to be one standard deviation below. But 68 total are going to be in there. Okay? If I go out another standard deviation unit, so I go 2 standard deviation units below, so maybe I'm out about here now. Again, I'm not drawn to scale necessarily, okay? All right, so now I'm out. This is 1 standard deviation unit. This is 2 standard deviation units, minus, plus 1, plus 2. All right, so now in this whole chunk in here, let me hatch it the other way. All right, so that whole piece from -2 to +2, there's just about 95% is in that whole big area there, okay? So if you're 2 standard deviation units above or below the mean, okay, so what's left is 5%. We've used up 95% in here. So that means there's 2.5% of the population is out here, and 2.5% of the population is out here, right? Now let me just translate that into IQ for you for a second to make it a little bit more clear. IQ is usually scaled in such a way that the mean is 100, and the standard deviation of IQ is 15. That's the way it's usually scaled. All right, so that means what? That means here's the mean, 100, right here in the middle. And then if I go up 1 standard deviation, that's an IQ of 115. If I go down, it's 85. So that tells me that in the population, 68% of the population's IQ is between 85 and 115, right? 1 standard deviation unit above and 1 standard deviation unit below. If I go out another 15, so I get down to 70 here on the low side, and I go up to 130 here, now I know that 95% of the population is between an IQ of 130 and 70, okay? All right, so now we're getting, if you're only 2 standard deviation units above, we're getting into some pretty rarefied territory. Only 2.5% of the population has an IQ of over 130. Okay? What if we go out 1 more standard deviation unit? Let's just go out 1 more. Okay, so now we're out to, I don't know, about there. Okay, so now we just got this little bit left right here. Same thing on this side. Draw my line out a little bit further. There we go. Something like that. Okay. All right, so now we're way out here, and what's left in this little chunk? Well, now to get when we're out 3 standard deviation units, now we've captured 99.7% of the population. 99. So that means there's only 0.15% of the population in this little area here. That's a IQ of 55 down on this end and 145 up on this end. There's only 0.15% of the population that has an IQ of over 145. That's a very small amount. That means if your IQ is 145, that means your IQ is higher than 99.85% of the population. So when you hear someone telling you that their IQ is 160 or something, you have reason to be suspicious, okay? Because, boy, this is a little teeny tiny group in the population, and it's pretty unlikely that somebody's going to be way out there, 3 standard deviation units above the mean, okay? That's always the case for anything that's normally distributed. Now, luckily for us, it turns out that many, many things in the world have normal distributions. And so that gives us a lot of leverage in terms of figuring out what's going on with an estimate of something that we have, okay? Because we know an awful lot about how that variable is distributed if we can assume that it's normally distributed. One other characteristic of the normal distribution is that the mean and the median and the mode are all the same if something is normally distributed. Okay? We can see that's the mean right here. If I add up all the scores above and below, I'm going to end up right here. We can see that half of the cases are above and half the cases are below, so that's the median. Okay? And we can also see that this value right here is where the most cases are. It's the highest level in the curve, and so it's also the mode. That's one of the cool characteristics of the normal curve. Now, this is going to relate back to us doing testing of the question that we're interested in a little bit, because it's going to help us figure out the chances that we're wrong. And that's really what we want to do when we're doing statistics. We want to figure out what the chances are that we're wrong. And we'll see that we are going to be willing to tolerate, you might be willing to tolerate different levels of how wrong you are, how likely it is that you're wrong, okay? There's always a chance, and you can try to minimize that in various ways. But you have to figure out how much tolerance you have for being wrong, okay? In many, many statistical situations, we use what's called the 0.05 level. The probability that we're wrong, the chances that we're wrong is 0.05, which means 5%. We're willing to be wrong 1 out of every 20 times we draw a conclusion. That's what we're typically going to use. It's just a convention. You don't have to use the 0.05. You can use 0.04. You can use 0.1. You can use whatever you want. But when you move that around, you're changing the chances that you're wrong in your conclusion. That's what you're doing with this. We're going to stick with this throughout the course, but there's situations where you actually might want to use a different value. But we're not going to get into that in this course because we want to focus on some other things. But we just want you to know that when you're working at the 0.05 level, which we're going to do in every single test that we make throughout this course, we're going to allow ourselves to be wrong 1 out of 20 times, okay? When we do that, that's what we're talking about. So when we say 0.05 level, that's the level of sort of competence that we have in the conclusion that we're making, okay? Okay. That's all related to how this distribution is set up. And so if we're talking about the 0.05 level, we know that we're finding something that's outside of this middle gut of the distribution. We're going to show you how that works in a little bit when we start doing some tests.